we had learned what is potential energy, what is potential. So that day I had discussed that whenever we talk about potential energy or potential whatever, so every time you have to fix a reference point or reference where the potential will be zero initially. Okay, where the potential will be zero, and with respect to that reference, you have to calculate the potential or potential energy. So that day we had defined what is potential. So potential in this case, electrostatic potential we are learning. Electrostatic potential. Okay. So look, when we have certain charge over here, this is called source charge. It will create a field around it. So if I bring another small charge from infinity, suppose from infinity to this point somewhere here. Okay. So this is also positive charge. This is also positive charge. So there will be repulsive force between them. So if I bring this charge from here to here, obviously I have to do some work. So you have to apply some external force. Okay, that external force is nothing but the force you experience, that is Q into E, the electric field. Q into E, that is the electric field which exerts the force, like the force which exerted by the electric field created by this charge. This is the force, and this much amount of external force you have to apply on this charge to bring here, and obviously you have to do certain work. Suppose this distance is d, so you have to do certain work. So this work, since it is actually conservative force field, it is conservative force field, conservative force field. Electrostatic force field is conservative force field, and whenever we talk about potential energy, obviously you have to uh, understand that that force field is conservative force field. Okay, whenever we talk about potential energy or potential, so potential energy or potential relevant for conservative force field. So when you do work against the electrostatic repulsive force, which is actually acting like this, this positive charge is repelling this guy Q, and at the same time this charge also repelling this. So this work done is actually stored at this position. Okay, at this position as potential energy. Okay, so that is called potential energy. Now potential energy, if you bring, see, Q charge, now if you bring 2 Q charge, you have to do more work. If you bring 4 Q charge, you have to do another again more work. That means at the same point, if you talk about potential energy, that can be anything. That can be anything. That means it can have a work done W1, it can have work done W2, it can have work done W3. That means at this point, potential energy is not a unique uh, quantity, physical quantity. It is not a unique physical quantity. But I want to define a term which will be unique quantity. Whatever charge you bring, okay, or at particular position, that quantity will be invariant. That will not vary. Okay. Okay. However, you come, like if you come from this side, also it doesn't vary. If you come from this side, so this point will have a constant value of that physical parameter that we have defined as potential. Instead of potential energy, we have defined potential. So potential has been defined as work done per unit charge. Work done per unit charge. So which is denoted by V. So this is the potential, electrostatic potential. So now in the last class we had defined, or we had derived a potential, how to calculate potential due to a point charge. Okay, how to define, like how to derive potential due to a point charge. Okay, due to a point charge. So if you remember, uh, we have derived that, and I'm not going to derive today. I just will write that. So that will be, if suppose the Q charge will create a potential over here at r distance. How much potential it will create? It will create a potential that is Q by 4 pi epsilon naught r. If this is the distance. If it is r2, then it will be r2 over here, r1 over. So that depends on r. So potential depends on r as or distance inversely. Okay, so potential vary to the distance inversely. So that is what we had discussed. Now today we'll see, if we have an electric dipole, what will be the potential due to that electric dipole? Okay, the screen is coming. Okay, yeah. So this is the, see, are you able to see this? So this is the dipole, electric dipole, due to which I have to calculate potential. I'll just take a snap of this and then I'll discuss over there in the presentation. Priyadarshini, are you seeing my presentation now? Are you able to see my presentation?
Yes, sir.
Nice. Okay. Now look, I have a dipole. I have an electric dipole. So electric dipole, how do we define electric dipole? In the previous chapter we had done that. If you have positive charge, like equal and opposite charge, if this is plus q, this is minus q. Okay, if there are two equal and opposite charges separated by, they are separated by a distance. Okay, separated by a distance d, suppose here 2a it is written. If it is 2a, then these two charges together will be called as an electric dipole. Pole means monopole. There are two things: monopole, that means only one polarity, either positive or negative. But when dipole, when we talk about dipole, the system will be having, the system, charge system will have both the types of charges, either positive and negative. Both the charges will be there, and obviously electric dipole is defined as this way, that if you have two equal and opposite charges and separated by a certain distance, then that system is called an electric dipole. Okay, and that electric dipole will be a vector quantity, like it will have dipole moment. Physical and quantity, like measurable quantity, is dipole moment for this electric dipole. So physically measurable uh, term is actually dipole moment, which is defined, actually denoted by p, and this is a vector. And how do you define this? The magnitude of the charge, okay, magnitude of the charge q into the separation between these two charges, so 2a. And since this distance is, we'll just see that the dipole moment will be having direction from negative to positive direction. Okay, see here it is shown towards negative to positive. Okay, so this is a dipole moment vector, and it has magnitude q into the distance of separation between the charges, that is 2a, q into 2a. So if I write p, magnitude of p, so it will be q into 2a, or 2aq. This is the dipole moment. And how do you, what is the unit for this? So this is coulomb and this is meter, coulomb meter. Okay, coulomb meter. This is my dipole moment. Now look, if I have this dipole having dipole moment P, and for this dipole, I have to calculate potential at this point, potential at this point, P. So how do we calculate? Just recently we have learned how to calculate potential for a point charge. If I have point charge Q, so potential for this point charge Q, it will be how much? Q by 4 pi epsilon naught into the distance where I am calculating the potential. Okay, for this charge. So this is how I know how to calculate the potential for a point charge. So now look, so this dipole has two point charges. That's all. If I consider this dipole having two equal and opposite point charges, so look, I have drawn here the distance C. I have to calculate the potential at this point due to positive charge. At the same time, I have to calculate the potential due to this negative charge also, due to this negative charge also. So at this point, see, I have told you that potential can follow, it follows actually superposition principle. That means if you have several charges, then you can calculate the potential. This is valid for field also. Superposition principle, principle of superposition. So if you have two charges now, you can calculate the potential for both the charges separately. For Q, I'll plus Q, I will get some potential here at this P, and plus for minus Q charges also I'll get some potential over here. Now if I take, this is scalar potential, actually scalar quantity. Potential is a scalar quantity, even though it has like direction, like high potential, low potential direction is there, but still potential is a scalar quantity. So if I take the scalar sum, okay, so V1 plus V2, like that, if I take the sum of all those, okay, then I can get the potential due to this dipole itself. So do you understand what I am trying to say? I have two charges, positive charge this Q, I have negative charge minus Q. If I can calculate the potential due to these charges individually at this particular point P, then if I take the algebraic sum of these two potential at this point, then the sum will be the total potential due to this dipole. Okay, that is what we are going to do. Now look, if I write what is the potential at this point, then potential will be, see, I'll write Q by 4 pi epsilon naught. What is the distance from Q to P? That is R1. Now look, this charge is minus, so potential will be minus. So I'll write Q by 4 pi epsilon naught R2. Actually, this is the potential. Okay, this is the potential at this point. Now the question is, this R1 and R2 is not given to you. You have been asked to calculate potential at point P, which is a distance from the dipole as R. This is the distance from dipole. This is R distance. Okay, at R distance. But this is not say R1 is not given, R2 is not given. So what I have to find out? I have to find out the value of this R1 and R2 in terms of this R and this A. Are you people able to hear me? Are you people able to hear me?
Yes, sir.
Oh, nice. Yeah, I was getting some huge sound. That's why I thought, let me see. Okay, no problem. So, see, I know the see, I know the quantity A. A is the half of the length of the dipole. Okay, length of the dipole. R I know. This is the distance. Suppose it will be given some 5 meter, 10 meter, whatever. So that is the distance from the dipole, and that we have taken from the middle point of the dipole. So from O to Q, see this is A, again this O to minus Q, this is A. So I have to find out this R1 and R2 in terms of A and R. So if you remember the triangular law, okay, law of triangle of vector addition. So from there we can find out, actually, see R1 square, what I can write, magnitude of the vector, this R1. If you have so you can see this so from here we can write from the law of triangle, okay, law of triangle of vector addition. From there I can write, see I can write R square plus A square minus 2AR cos of angle between A and R. See, A is this one and R is this one, so the angle is theta, so cos theta I can write. Similarly I can write R2 square, okay. So in this case what I can write is, see this also R square, this is also A plus A square, see minus of 2AR. Now what is the angle? This angle is how much? This is 180 degree and this is theta, so it will be pi minus theta, right? This will be pi minus theta. So cos of pi minus theta will give you a minus sign over here, so you will get ultimately R square plus A square plus of 2AR cos of theta. Okay, so this is the thing you will get. Now see, I'll just go to the next page. So I have got V is equal to Q by 4 pi epsilon naught. If I take common this part common, then I have to get 1 by R, R1 minus 1 by R2. So this is the term I have to calculate from here. So I have got, see, I have got R square is equal to A square, sorry, R square plus A square. First one was plus, sorry, minus we had taken, just a minute, minus 2A R cos of theta, okay. So look, this I can do a little bit of simplification. How can I do? So R square, I can take common, then I can write this is 1 plus A square by R square minus of 2A by R. This is cos of theta. Can I do or not? I can do that. Now look, here you have to make some assumption. So you have positive charge, right, and you have negative charge here. See, the separation between the charges, positive Q and negative Q, this is actually very small. This 2A is very small compared to the distance R. Okay, this is the assumption we will take. That means the assumption is this, that A square, A is much less than R. Then what will happen? So A square by R square will be much less than 1. Okay, much less than 1. Okay, or I can say this can be negligibly 0. Okay, so see, so from here what, like, see, I'm just doing the approximation. R square 1 plus, sorry, this will be minus, see this term will go off, this term will be, I will be neglecting this term because this is the assumption we have taken. The dimension of the dipole is much lesser than the distance where we are calculating the potential due to that. So this will be cos of theta. Okay, now I have to find out 1 by R. Okay, R1. So I'll just do it 1 by, see, if I just take R, so this will give you whole to the power minus half. Okay, if I do 1 by R1, sorry, whole to the power half it will be. If I do that, so look here what I'll get. So this will be 1 by R, and this I can write 1 minus 2A by R cos of theta whole to the power minus half. You just look from this point, see from this line to this line, I have done 2-3 things here. See, I have just taken square root first of all, so half will be here. So if you just take r square out of square root, so it will be r. So if I take 1 by r1, so I get 1 by r, and see this one square root, so square root will be down, so I have taken it up, so you'll get this one. So I'll just do little more simplification. So before that, I'll just remove this portion so that I can write it here itself. Okay, so now look, this I can write 1 by r1 nearly equal to 1 by r, and I'll just do, see, since your a is much less than r, so a by r also will be much less than 1. Okay, this also will be less than 1. So see this factor, this one, this particular portion, I can just make some assumption. I'll write first, then I'll say why I have written that. See, I can write this as 2a by r cos of theta, half will be multiplied here. So from where I have written this, so I'm just doing the series expansion, and you know, like there is a formula. I'll just write in the next page. See, there is a formula. If you have 1 minus x whole to the power minus n, and if your x is less than 1, so I can write this as a series. See what will be the series? First will be, see, first time 1 will be there, then see, then it will be plus of the power n and x. Then what will be happening? Then again n square by 2. Okay, n square by 2, yeah, n square by 2 x square, like that it will go. Okay, it will go like that. Understand? So are you understanding? I think, yeah. So this is the thing. Okay, I think it will be n only. It will be n x square by 2, like that it will be. Okay, n x square by 2 and all. This will be the series. Okay. So if I see, I have this one 2 into a by r cos of theta whole to the power minus half. So this I have taken as minus n. Then what I have written? I have written up to this approximation because see, a by r, a square by r square, this is the x. Suppose this is, the whole thing is x. So if here a square by r square, again it will be negligible, by negligible, right? Negligible quantity. So I am just taking approximation up to the first order of this. Okay, first order of this. Okay, higher order I am just neglecting. So this is how I have written. Look here, I have written this. What I have written? I have just multiplied half with this term. So finally what I'll get, 1 by r, this will be nearly equal to 1 by r plus, so this 2 goes off, so a by r cos of theta. Okay, this is the thing you will get finally. So this I have got for 1. So I can get for the same, see, similar way I can get for the other also. I'll just write it for the other one. See what I have for the other one. I have, see, I have r2 square is equal to r square plus a square, and here it was plus 2ar cos of theta. So similar fashion I'll do r square 1 plus 2 by 2a by r cos of theta, then it will be a square by r square. This term we will neglect now. So now we'll do r2. This will be nearly equal to 1 by r, and here see this will be cos of theta whole to the power minus half. So if I do the further this series expansion here and take up to the first order term, so it will be minus, the half will be multiplied with this 2 A by R cos theta, and 2 goes off, so you will get here 1 by R 1 minus A by R cos of theta. See, for the previous case you have got plus over here, and now you have got minus. So I'll just write all of them. See, look here, I have to do q by 4 pi epsilon naught 1 by r1 minus 1 by r2. So I'll just put the value over here. 1 by r1 what I have got, and 1 by r2 what I have got. So this is actually, see what we have got here, 1 by r, okay, 1 by r. Then for r1 it was plus, okay, plus 2a by r was there, sorry, 2 not 2, a by r was there, okay. So r square was, it will be actually r square now, okay, it will be r square now. And see, because you have to multiply this, no, you have to multiply r inside, okay, for r1. Look, you have to multiply this, so it will be 1 by r plus a by r square cos of theta. So this thing I am going to write over there. So this is cos of theta. And the previous case, like for 1 by r to what we have got? We have got 1 by r minus, there was minus here in this term, so it will be r square cos of theta. Look, this will cancel each other. So 1 by r, 1 by r cancels each other. So I have got q by 4 pi epsilon naught, and this is actually 2a by r square cos of theta. Look, so if I multiply 2aq, that will be magnitude of p, because p is actually 2a into q. So if I just put it here, this whole term p, so you got p cos theta in the numerator, in the denominator you get 4 pi epsilon naught r square. So you can see for a dipole, the potential, how you got the potential now, how you get the potential? See, 1 by r square. See, this is the voltage, okay, this is the potential due to this dipole. Look here, see, I'll just clean everything. So what is the potential you get? You get p cos theta divided by 4 pi epsilon naught r square. R is this distance, okay, this distance is r, okay. Now, so you can see, in case of point charge, you have got potential q by 4 pi epsilon naught r with the distance. But for a dipole, what you get? You get, see, r square. For dipole, potential actually varies as 1 by r square. And we had seen electric field for a dipole was varying actually 1 by r cube. And in case of point charge, it was varying, how it was varying? It was actually varying as 1 by r square, like this, okay, q by 4 pi epsilon naught r square. Okay, so this is the thing, okay. So I can write, see, I can write this term little more, uh, like, see, like little more fancy way. How I can write fancy way? See, this is the, so if I take the angle, see, this is p. See, p cos theta I can write in this way: p vector dot n cap. N cap means what? The direction of the dipole, okay, or unit vector, any unit vector, okay. I take any unit vector, and this is the dipole direction, and the angle between them is, so if you take this dot product, you know, like you have to take the magnitude of this and cos of angle between them. This will be the result. So see, this magnitude of the unit vector will be 1. So I can write p cos theta as p dot n cap. Do you understand this? Nikhil, Priyadarshini, do you understand this? P cos theta I can write p dot n cap. Do you understand this? Or shall I repeat? See, because n cap, see, if I write this p vector dot n cap, okay, that means a dot b. A dot b means modulus of a, okay, into modulus of b, and the cos of angle between them. So angle, suppose angle between them is theta. So okay, so I can see. So this will give you 1. This modulus is 1. So finally what you get? This modulus, suppose p. So you get p cos theta. Okay. So p cos theta I can write as p dot n. P dot n cap. So finally what you are getting, the potential at r distance away for the dipole is p in dot n cap by 4 pi epsilon naught r square, or p cos of theta by 4 pi epsilon naught r square. Okay, so you can understand that this potential not only depend, see, not only depends on the distance, it depends on the orientation also. So for a dipole, even we have seen in case of electric field also, electric field does not only depend on the distance. For a dipole, it depends at which angle, which place you are calculating the electric field or potential. So electric field and potential for a dipole depends not only the distance, it depends also with the orientation or the places you are calculating the electric field or potential. Now look, so if this cos theta, if theta is pi by 2, what will be the potential? So potential will be 0. If theta is pi, what will be the potential? That will be minus 1. If theta is 2 pi, 2 pi, what is the potential? 2 pi or 0. What is the potential? That will be actually, this will be actually, yeah. So not minus 1, it will be actually p by this, okay, p by 4 pi epsilon naught r square, and it will be plus p by 4 pi epsilon naught r square. Okay, so the potential actually varies from minimum to maximum to 0. Look here. So when the angle is 90 degree, the angle between the direction you are calculating the potential and the p. If this is 90 degree, this is the direction suppose. I want to calculate potential over here. So at this direction potential will be 0. Okay, potential will be 0. So if I calculate potential over here, so the angle is pi. So potential will be minus p by 4 pi. So this is the minimum potential energy you can have. This is the minimum potential. What is the maximum potential energy? If you have, see, your dipole is parallel to the direction where you are calculating. Okay, if they don't have any, so that means if you calculate the potential on the dipole axis itself, you will get the highest potential. Okay, okay, look. So, but always, okay, we'll see that. And as I said, there will be always some reference point. So where the reference point is in this case, the potential, where potential is 0 or potential energy is 0, that is the potential, uh, that position is called the reference point. Okay. So what is the reference point here? Pi by 2. So it is written in your book. You can now read it carefully, and then you will, yeah, then it will be very clear to you again. Look here. So the potential of a dipole depends not only on r, it depends on the angle between the r and the dipole moment. Okay, and in this case dipole, see, in case of electric dipole, the potential depends on 1 by r square. In case of point charge, it depends on 1 by r. So this was our like whole knowledge. See, here potential theta is equal to pi by 2 means potential will be 0. Okay, potential will be 0. When theta is equal to 0, potential will be positive. When theta is equal to pi, potential will be negative. Okay, all right. Now look, so can I get you people? Okay, I don't know. Nikhil is not there. What happened to Nikhil? Priyadarshini,
Don't know.
are you able to hear? Are you able to hear me so far?
Yes, sir.
Nice. Okay. I'll just put a message to Nikhil. I'll just put a message to Nikhil, and then we'll just learn the next portion. Okay. So we have now calculated, or we have learned so far how to calculate the potential due to a point charge, and then we have seen how to calculate uh, potential due to uh, a dipole at any point, and we have learned that oil. Now we will see, if I have, instead of a single point charge, if I have system of charges. Look in this figure. So there are see five charges: Q1, Q2, Q3, Q4, like that. So in this case, how to calculate a potential at particular point? I had already told you this, that it will also follow the principle of superposition. Just a minute, I am getting a call. I think this is Nikhil only. Hello, hello. Yes. Sorry, sir. Are you Nikhil's father? Oh, okay, 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 okay. Thank you. Okay, I think your father called me. Yeah, Nikhil.
Sir,
Hello,
sir, yes, sir.
hello, Nikhil. Are you able to hear me? Okay. Are you not there in the WhatsApp group?
Sir, I am there, sir.
Okay. Could you see the message? I
Sir,
just
there was
few
a
minutes
power cut, so
back
only
I
I.
wrote in the WhatsApp. Okay, okay, no problem. Okay, no
Yeah.
problem, no problem. All right, all right, all right. Okay, good. Okay, so so how much have you had? When did you leave? Did you see the whole derivation for the potential due to the dipole, electric dipole? Have you heard that whole thing, or where did you leave? Then I'll just tell you a few points. Did you see the whole derivation for this or not? Nikhil, I am talking to you. Nikhil, are you able to hear me? Priyadarshini, are you able to hear me?
Yes, sir.
What happened to Nikhil? Nikhil, are you able to hear me? Okay, then yeah, I am not getting your response. Can you just talk to me? See this derivation. I don't know whether you have all like heard. Priyadarshini, when did he leave? In between, he left
He's there.
during this. No, he is there now. I am asking whether he has had like learned the whole derivation or not
I
for the
haven't
previous.
noticed, sir.
Okay. You haven't noticed. Okay, no problem. Nikhil, can you speak to me?
Yes, sir.
Okay, I don't know, or maybe I'll write to him. Okay, I'll just go to the next part. Okay, I'll go to the next part. So now we'll see when we have a system of charges. That means not only one charge or two charges. I have many charges. For that case also, you can calculate the potential separately. Like for charge 1, I can calculate Q1 by 4 pi epsilon naught R1P. Like in this case, suppose at P I have to calculate the potential for this system of charges. I can calculate the potential separately, okay, for Q1, for Q2, Q3, etc. And then I can add the potential to get the total potential at this point P. Okay, so this is how we can uh, do for a system of charges. Now so there is an example. This you can see because it is solved. I'm not going to talk about this now. Okay, but this can be a good problem. Okay, this can be a good problem. You just see, this is an important problem for you people. You just read this thing. Okay. Okay. Now we'll see here. This example also is very important. Look, uh, this is positive charge and this is negative charge. So here you have to find out. She show the fields above positive and negative. Okay, give the sign of the potential. Okay, give the sign of the potential difference. See, there are 2 points in this case, Q and P. So what is the sign of this potential? P minus Q. So who knows if which one is so whether this is positive or negative? And in this case, whether this which one is VA minus VB or VB minus VA, whether positive or negative. Okay, so this you can see, like in this case, negative, right? This is the negative one. So the potential will be with a negative sign, minus Q by 4 pi epsilon naught R. So as you go near and near 1 by R, that denominator will be smaller. Denominator, sorry, big, smaller. Yes, smaller means negative quantity will be blowing up. Okay, that will be more. So VB minus VA, this will be a positive term. Here also VP minus VQ. In this case, look, in this case also, this will be actually positive. Okay, you just analyze by yourself and see the answer later. Okay, we'll go to the next portion. It is called actually equipotential surfaces. So this is also very important topic and very important to understand also. I'll just copy this figures. Okay, just a minute. Okay, so see, you have seen that if I have a point charge, so how the field looks like radially outward, and how the potential we have got for point charge, this is epsilon naught r. That means if I calculate potential for a charge here at fixed distance r in all direction, look in all direction at fixed distance r, okay, so the potential will be actually the same. Okay, at see in which direction ever you calculate for a point charge, I am talking point charge. That means what it has? It has a spherical symmetry. So this, if I can draw a sphere, okay, if I can draw a sphere making the point charge as center like this, if I can make a sphere, so the spherical surface which is 4 pi r square, if this is r distance away, 4 pi r square is the surface area. Okay, on each point on the surface area the potential will be constant, same. If you go from here, so if the potential is constant, so from here to here, so if the potential is v here, v1, here also v1, if you go here it also v1, this also v1, everywhere the potential is same. So for a point charge, the spherical surface, see around that charge has equal potential, that is called, so this surface, this kind of surface are called equipotential surface. Equipotential surface, that means at each point of the surface will be potential will be equal. What does that mean? Suppose I take a plane surface like this, so if this is my a point, this is my b point, okay, so if I know the potential for this point va and potential for this point is VB. Actually, this VA is equal to VB. That means there is no potential difference. Okay, there is no potential difference. At each point on this surface, if this is an equipotential surface, at each point there will be same potential. Okay, equipotential, equal potential at each point on the surface. So these potential surfaces for point charges are, point charge is what? How does that look like? Spherical surface, okay, or spherical cell. Okay, so for a point charge, how does the potential surface, equipotential surface look like? They will be concentric sphere. Okay, concentric sphere. See, this is one equipotential surface. This is another equipotential surface. This is another equipotential surface. This is another one, and this is the last one. So there are concentric circles, or sorry, spheres. So for a point charge, equipotential surface will be concentric spheres. So there will be a question. So there will be a question. Suppose in your exam paper, they'll ask you to draw the potential equipotential surface for a point charge. So then you have to draw like this, concentric circle. You have to draw concentric circle, but these are not actually circles. These are spheres. These are three-dimensional bodies. So these are concentric sphere. You have to say the equipotential surface for a point charge will be concentric sphere, keeping the charge at the center. Concentric sphere. So we have defined potential as work done per unit charge. So work done will be Q into V. But if suppose on the equipotential surface, as I was saying, A point here and B point here, so both the point has same potential, right? V. Okay. So if I take one point charge, positive charge, small q, from A to B point, what will be the work done? What will be the work done? Can you tell me? work done will be 0 because you have to have say work done means in this case it will be potential difference between these 2 points. Okay, VA minus VB or VB minus VA, whatever. Okay, so since there is no potential difference, VA and VA and VB are equal for an equipotential surface, so the work done will be 0. This will be 0. This time will be 0. So your work done will be 0. So what we get? One property we have got: work done to take a charge, any charge, positive or negative, from one point to another on or in equipotential surface potential surface. So work done to take a point charge or any charge from one point to another point in equipotential surface will be 0. Okay, will be 0. This is an important point to remember. Okay, in equipotential surface, if you take from one point to another point, okay, charges. And one more point you look here. So how the electric field will be? So this is first property. Second property, see, look here, if I draw electric field lines, see here, electric field lines are radially outward. So how is this actually at this point? What is the angle between this? This is 90 degree, right? So direction on this particular surface will be tangent to it, okay? And if I draw the radial vector or radius vector, so that will be perpendicular to that tangent, okay? That means the electric field always will be perpendicular to the potential equipotential surface at every point. At every point of the equipotential surface, the electric field line will be perpendicular. Okay. So electric field lines electric field will be perpendicular. Okay, perpendicular to equipotential surface. Okay, equipotential surface. Okay, so this is the thing. So this sign, see, sometime this sign means perpendicular. Okay, and if sometime if this is written, so it will be parallel. Okay, two parallel line, parallel, or sometimes EL also people write with that. A perpendicular, this with a R. Okay, so electric field will be always perpendicular to the equipotential surface. Okay, so now if my electric field is given, so suppose electric field, suppose this is my x, y, z, this Cartesian coordinate. Now if I have been given uniform electric field, which are actually parallel line. Uniform electric field means equidistant parallel line. This is how you can denote the uniform electric field. Okay, uniform electric field can be denoted as equidistant. So this is D, this is also D, this is also D. Equidistant parallel line. Okay, suppose my uniform electric field is along the x-axis direction. Can you tell me, or can you draw what will be the equipotential surface? This is y direction, this is z direction, suppose, or other way. This is z, this is y. So which surface or which plane, in which plane you will be drawing the equipotential surface for this case? You have to remember that electric field will be perpendicular to the equipotential surface. So that means in this case, if this is z, this is y, so your yz plane, look, this yz plane is perpendicular to the electric field. So this will be your equipotential surface. Okay, and this can go up to this way. It can go this way also up to infinity. Okay, that doesn't matter. Okay, so this is actually equipotential surface for the uniform electric field which is directed towards x direction. Okay, this is Ex. This is given in your book. You can see that. Okay, look here. So since we have started the class at little late, I'll go another 5 minutes. Okay, another 5 to 10 minutes. Is that all right for you people? Both of you, can you just respond to me? I think another 10 minutes I'll take because we have started the class late. Priyadarshini, can you respond to me?
Yes, sir.
Is that all right for you?
Yes, sir.
Nikhil, is that all right to you if I
Sir.
go another 10 minutes?
No problem. Yes, sir. You can.
Okay, fine. Okay, so yeah. So see, the electric field is along the x direction. Then this will be the plane perpendicular to the electric field direction will be the equipotential surface. So we have got two properties for equipotential surfaces. See, equipotential surface will be having equal potential at every point. That's why you don't have to do any work to take one charge from one point to another point because there is no potential difference. There will be no work done. Okay, and electric field is always perpendicular to the potential surface, equipotential surface at each and every point. So you look here, these are the type of see the equipotential surface drawn for a dipole. See, this is for dipole. This is negative charge, this is positive charge. If they are together, see, since these are actually point charges, so you can draw concentric circles. Sorry, concentric spheres. I would say concentric spheres. For positive point charge also, I would draw concentric sphere. But look, these charges are actually there is influence. So when I draw potential, equipotential surfaces for this positive point charge, I have some influence from negative charge. At the same time, when I draw equipotential surfaces for the negative one, I have some influence from the positive charge. So that's why these are not exactly see, see they are not exactly the concentric. Okay, they are not exactly concentric. Their center. See these pairs. You can understand that their centers has been little bit shifted because these two charges actually attract each other. Point charge and see negative and positive. Okay, this their like electric fields they will be actually so these are attracting each other. Okay, that's why at this point see in between them the space between the spheres. Okay, constant like consecutive surfaces, spherical surfaces, the space between consecutive surfaces will be less. See, in this way, this is actually having less space than this one between these two, less space is there. But see, rear side you look, rear side, the space is actually large. So, in between them, the region in between them, for both the charges, the equipotential surfaces will be having lesser space or the density will be more, okay, in this region, whereas the rear side, see this side and this side, the spaces are actually more. Okay, this is because of the attraction. Now if I take two positive charges, see because of repulsion they will push each other. So that's why, so this is positive charge, this is positive charge. Okay, so in this case also the equipotential surfaces are not concentric circles or concentric spheres. The spheres got actually displaced, or you can say oval shape. Okay, this become oval shape, and you can look that the region between them actually both the surfaces has different like more space between the consecutive surfaces. Okay, consecutive surfaces. Okay, so this is what from here. Now look here, we'll be deriving the relation between electric field and potential. We'll be deriving the electric field and potential. I'm not writing. If I write, I may take little extra time. I'll just read from here and make you understand from this only. Okay, look here. I have taken here two equipotential surfaces. Okay, two equipotential surfaces. See, one has potential. The upper one has the potential V plus del V. The lower one has potential V. But each point on this potential surface has the equal potential. Okay, equal potential. And the top surface also, see this surface, this one, that also has this is equipotential surface, means at each and every point the potential is V plus del V, V plus del V. So these are two equipotential surfaces. Now I am taking 2 points. See one point. See, this is the surface A. Actually, this is the surface one surface. This they have, the difference between the surfaces is actually delta L. Suppose the difference between the surfaces is delta L. Okay. Now, if I take one positive charge, if I take one positive charge and take the charge from P to A, see in this case electric field is actually directed in this way. Okay. Look here, I have just taken arbitrarily that I am taking this direction of the electric field arbitrarily from A to B side. Okay, or A to P in this direction I have taken. Okay, and the DL is actually perpendicular distance between these two equipotential surface. They are actually one top of another. Okay, if one is at the ground, another one, the another surface having V plus delta V potential, that is actually delta L height away. Okay, so look, in this case, if I take a point charge here, okay, imagine that unit positive charge is moved along the perpendicular, along this perpendicular direction. Okay, from B to, from B surface to A surface, or directly from P to A. Okay, from B to surface A. Okay, so now if I do that, see this, these two surfaces are equivalent to surfaces, but these two surfaces have certain potential difference. If I say VA minus VB, there will be certain value. Okay, so since they have potential difference, I have to do some work. So I am doing work against the electric field. See here, the force is the electric field and the displacement is delta L. Okay, if I know the potential electric field between these two plates, then I just multiply delta L with the electric field to get the work done. See here, I can get it. This is the work done. Now, from the definition of the potential also, from the definition of the potential also, we know the work done will be Q into V. And here, what is the value of Q? I have taken unit positive charge. So the unit positive charge, that means the Q is 1. So I can write simply the potential difference between them as the work done. So I can write the potential difference between them as the work done. See, I can write V minus V plus delta V, because I am bringing that from the P to A, okay, from the upper surface to lower surface. So I'm thinking that A has greater potential. Just imagine. So I am taking the difference between the potential VA minus VB. So I can write V minus V minus of V plus delta V. So you'll get minus delta V is the work done. Now, if you take the modulus of that, see this delta, see this is E into delta L, that is also work done, and this is also work done. So they are same work done. I can write in a equation. Okay, I can just equate them. Now look, if I want to calculate what is E, I can write minus del v by delta L. Okay, delta v by delta L. So from this to, okay, from this equation to this equation. Okay, so this is the electric field. Now look, since this delta v is negative, why it is negative? Because see, this is the higher potential, this is actually lower potential, but I have taken potential difference from there to there. Okay, so this is negative sign. So in this position, actually in this position, okay, you'll get actually positive. Okay, you'll get positive. In general, in the equation you have got minus sign over here, but see delta L, I have, see delta L has a direction from A to B, but I am bringing my charge from P to A. Okay, A to P is delta L positive. In the opposite direction, delta L will be negative. So in that way also we can say that this term will be ultimately positive. Anyway, positive or negative doesn't matter. What matters is actually these two conclusions. You look here, these two conclusions. From this equation, actually this derivation used to come in the exam. Okay, in the board exam, actually there will be a question: derive the relation between the field and potential. Then you have to write this. Okay, and what is the conclusion from here? They will ask what is the conclusion from this derivation you get. So the conclusion, actually there are two conclusions. One is the electric field is in that direction in which the potential energy, or sorry, potential decreases the steepest. That means the electric field, if I take this as positive, so electric field will be more if the delta V is more. Okay, or I can say electric field will be more if the change in the potential is more, right? Del V by del, if this value is increasing, then electric field also will be increasing. That means your electric field direction is in that direction. And if I say negative sign, del V by del L with a negative sign, then I can say the electric field, actually this is the original relation. The E is equal to minus del V by del L, not positive. There will be, in general, there will be negative sign. So negative sign means what? If this decreases, okay, if this delta V decreases with the position or with the distance, then this term will be positive. Okay, that means electric field will be increasing in that direction in which direction the potential decreases. Okay, look, this conclusion you might be having actually difficulty to understand what this line means. The electric field is in the direction in which the potential decreases steepest. That means if the rate of change of potential is more, then the electric field is more in that direction. And since there is a negative sign, so I can say this rate of change is negative means what? Decreasing, potential decreasing with, like the direction in which the potential is decreasing faster or steepest, electric field will be directing in that way. So look here, the electric field, actually the potential is decreasing in this way. Actually, if delta V is negative, I can say in this way. So according to my figure here, the delta V should be decreasing this way. Okay, when I go to, if this is actually a negative sign, negative delta, then it is decreasing in this way. Okay, if you are confused, let me just clear, okay, in 1 minute, that the potential, if delta V is negative, if delta V is negative, then potential will be actually changing steepest in this direction. Okay, A to P direction, potential is decreasing, right? V is getting minus. Okay, that's why potential will be decreasing in this direction. Okay, so the electric field will be A to P direction. Okay, this is what is written here. See, its magnitude is given by the change in the magnitude of the potential per unit displacement. If I take this delta L as unity, then you get uh, that the potential, see, electric field, magnitude of the electric field will be the change in the potential per unit displacement, and that displacement has to be done normally normal to the equipotential surface. See, this direction is normal to the equipotential surface. Okay. So up to this, okay, we'll stop it here. We'll learn the next part in the next class. Okay. We'll meet on again Wednesday. Okay. So see you guys on Wednesday. Okay. Okay. Bye, Priyadarshini. Bye, Nikhil.
Thank you, sir.
Okay. Welcome.